Okay, so here's another example for class 18, another problem out of Munson's book. A Boeing 747 aircraft weighing 580,000 pounds when loaded with fuel and 100 passengers takes off with an airspeed of 140 miles per hour. With the same configuration, that is, the angle of attack, the flap settings, etc., what is its takeoff speed if it is loaded with 372 passengers? Assume each passenger with luggage weighs 200 pounds, which is a pretty good, I don't know. Is that a good assumption? 200 pounds? Kind of wondering. I've seen how people pack lately. And what people weigh lately. Let's not judge. So anyway, I'll say that the lift in the first state, I'm calling 1 as the first state, is going to need to be 580,000 pounds. The lift in the second state is going to be 580,000 plus we're going to have an additional passengers, right? So we started out with a 100, so let's take 372 and subtract out 100. So this is going to be the additional amount of weight, and that's going to be 200 per passenger right there. So we end up with 624,000 pounds now in the new configuration. Right. If you take the, because the lift coefficient is non-dimensional, we can say that as long as everything is equal, we can write an equation like this right here, where you take the lift and divide it by the dynamic viscosity, dynamic viscosity, by the dynamic pressure with times the area right there, right? So this right here is like the dynamic pressure from Bernoulli and times the area, so that generates a force, and so this is a non-dimensional number. And we could say that's scenario 1, and here is scenario 2. And all things being equal, we could cancel out these terms and simply say, and rewrite this around, maybe say the velocity 2 is going to be equal to the lift 2 divided by the lift 1 times the velocity 1 squared. Or you could say that the velocity 2 must be equal to the square root of L2 over L1. And kind of end the square root sign, make it look like that right there, right? So we'll take the square root of our 624,000 and our 580,000 times on 140, and we find that we get 145.2 miles per hour. So we had to increase our speed by about 5.2 miles per hour because of the additional 272 passengers, which would have been right here, 272 passengers. This problem is maybe too short, so let's continue on with another problem here. There's actually 2 problems in one here. I've doubled up from Munson's right here. We want to show that for an unpowered flight, that means like we're going to use the airplane like a glider, for which the lift, drag, and weight forces are in equilibrium, the glide slope angle theta is given by the tangent of theta is equal to the drag coefficient over the lift coefficient. And then using that from this thing, we want to find if the lift coefficient of the Boeing 777 aircraft is 15 times greater than its drag coefficient, can it glide from an altitude of 30,000 feet to an airport 80 miles away if it loses power from its engines? So this is actually something that is possible, and sort of kind of an important thing to be able to do. So what you want to do in order to demonstrate this is to draw a free body diagram relatively carefully. And we will say, okay, so first the weight is coming out this way. And we know that that's going to be the same angle as this right here. Call it theta. And the lift we'll draw this way, and the drag we'll draw, well, I think I used the, yeah, I used the little kind of double back D thing going right here. Okay. So let me draw my X prime and Y prime directions right in here, and say the sum of the forces in the Y prime direction is going to be equal to 0. And so that's going to be the lift minus the weight times the cosine of theta. It's going to be equal to 0, right? If it's gliding. And the sum of the forces in the X prime direction equals 0. And we're going to have the drag, and then also we're going to weight times the sine of theta equal to 0. Okay? So here's where, in an earlier problem I mentioned that I suspect that they're using, even though it doesn't make sense, the planned form area here, because we want to divide this stuff out. We could divide one of these by the other thing, right? So we can set L is equal to W cosine theta, and we can divide by the drag and say the W sine theta. And actually, I probably want to do it the other way around, right? Because I want to get a tangent. So let me put the drag over the lift. Would have made a lot more sense. The drag over the lift. And this would have been the sine theta. And this would have been the cosine theta. Okay. And we know that that's going to cancel out and end up being the tangent of theta. So this guy on top is the drag 1/2 rho v squared a over CL, lift coefficient, rho v squared a. And like I said before, that those a's must be the same thing, because we're going to have all these cancel out and equal to the tangent of theta. And therefore, we could say that the tangent of theta is going to be equal to the ratio of the drag coefficient to the lift coefficient. And now we want to use that idea to say, well, how can this 777 glide? So let's draw him out this situation. Here's our airplane right there. Not a very good airplane, but it's still an airplane right there. I don't mean the 777, I meant our thing here. So let's say he's 30,000 feet. And he's making this descent. And so we're going to find that the tangent of theta is going to be equal to our drag coefficient over our lift coefficient, which we just said the lift coefficient was 15 times the drag coefficient, so that's 115. I can find this angle if I wanted to. I'm saying I can. I believe I can. Let's take 15 and to see. I'll take the A10 of that. Yeah. So let's say that's like a 3-point. Like in case we wanted to know, that's a 3.81. That's the angle of descent of the thing. But because of like similar triangles or that sort of thing, we can instead see that we have a rise that this is also going to be equal to 30,000 divided by d, right? So we don't actually need that angle, and we can just say we can figure out what d needs to be. So d needs to be 15 times the 30,000. Which ends up being 450,000. We can do that in our heads. Feet. And then if you divide that by 5,280 feet per mile, you end up getting that the distance this thing could go is 85.23 miles. Therefore, yay, we're okay, and we survived losing our engines and gliding. And this has actually happened before. So I'm going to come back with a couple more examples for class. plus 18 just to tide you over. Hope this is going to be helpful.